So, very good morning, students. And okay, so today we are going to solve one problem based on finite element method. So, on the screen, you can see in this problem what we need to find is we have to find the nodal displacement of a step bar. So, here let me take you to the through the problem. So in this problem, what is given? So in this problem, the displacement using direct stiffness method, we need to determine the right. So what we need to determine, we need to determine the nodal displacement. So we need to determine the nodal displacement for the step bar. So here in the sketch you can see this is the step bar, uh, and we need to find out reaction at support. So by taking E as Young's modulus, we need to take as 200 GPa. Now this is a step bar having two steps. So this area is given, which is 200 mm square, and here the area 2 is given as 100 mm square. And you can see this bar is fixed at one end, and at another end 10 kilonewton force is applied, and here at the mid of this first element we have 20 kilonewton. The step bar is of 100 mm. The first step is of 200 mm, and the second element is of 150 mm. Now here, first task is to discretize or divide this particular problem, physical problem, into the steps, or we need to convert this physical problem into analytical problem. So how we can convert? So first step is to discretize this or divide this into number of elements. Now here, normally we will have change in wherever there will be change in area, we will consider that as a element, different elements. So this is one different element, and this is one different element, right? Now here we have a force, which is, we have to define this force through a node. So for that I need to divide this particular section into two halves. So I can say I am having three elements. So this is first element, this is second element, and this is third element, right? So element is defined like this. So these are the three elements here. Now I am defining the problem into analytical form. So here I am drawing, this is fixed support. So one end is fixed, and we will have the entire length. So here I am defining the elements with the help of nodes. So this is node number. So I will start from fixed support. So this is node number 1, this is node number 2, this is node number 3, and this is node number 4. Right? So we have 4 nodes. Now in so here the elements are here. First element is in between node 1 and node 2. Second element I can define in between node 2 and node 3. Third element I can define in between node 3 and node 4. Likewise, we will have the second step for this problem is defining the connectivity table. So you can see this is connectivity table in which elements are written 1 2 3. We are having three elements, and now I am just defining the local connectivity between the nodes. So for the element number 1, connectivity, you can say element number 1 is in between node 1 and node 2. So that's why I am writing node 1 and node 2. Likewise, element 2 is in between node 2 and node 3, and element 3 is in between node 3 and node 4. So these are the local nodes for the element. So this was our second step for this problem. Now in third step, let us first write what data is given. So here you can see area 1 is given for node 1, area 1 is given, and area 1 and area 2 are equal. So I am writing area 1 and area 2 is equal to 200 square. Then we will have area 3. So as this is element number 3, so I can write area 3, which is given as 100 square, right? After that, length for the element 1 and 2 are the same. So I am writing L1 is equal to L2 as 100 Okay. Now we will have third length, which is given as 150 mm, and one more thing is given. So E value is given, which is Young's modulus, which is equal to 200 GPa. Okay, so all this data is given. Now after defining the given data, what I will do, I will define the stiffness matrix. So normally stiffness matrix can be defined as, I am defining stiffness matrix over here. Stiffness matrix, this is called as local stiffness matrix. So locally or normally stiffness matrix is represented by K value. So K will be equal to A E L divide into 1 minus 1 minus 1 and 1. Okay, so here A is area, E is Young's modulus, and L is length. So this is a global stiffness matrix. Now from this I can easily define the local stiffness matrix. So for K1, say for local element K1, I am defining stiffness matrix. So I am writing area A1, value of E is common for all. So I am writing AE into L1, and the same matrix I will write 1 minus 1 minus 1 and 1. So let us define the constants for K1. So for K1 I am writing the same matrix. K1 I am defining K1 as, so area 1, so area 1 you can see area 1 is 200 for this particular problem. Area 1 is 200 multiplied by E value is given 200 into 10 raised to power 3 divided by length of element is given. So length of element for this case is 100 AE by L into 1 minus 1 minus 1 and 1, right? So here I'm just writing, sorry, I'm just writing K value, K1 will be defined as, so I'm keeping something constant here. So I'm taking 10 raised to power 5 as a constant, which is constant I'm taking out, and I will write the remaining values. So remaining values are, here I have to write 4, 4, minus 4, minus 4 and 4. Okay. Now once again I will write, something is going wrong. I am not able to write, or it is giving a straight line. Okay, no problem. So this is how I have defined K1 matrix. Now as you know, K1, which is element number 1, is in between node 1 and node 2. That's why I have to write here column 1 and column 2. Likewise I have to write row 1 and row 2. So if I will define this element, it is at 1 1 position. So while defining the global stiffness matrix, I will combine this element and I will place this element to its position. Likewise, I will define K2 matrix. So K1 and K2, normally it is having all the values constants, values are same. So I am defining the values like 10 raised to power 5 common, and the same matrix 4 minus 4 minus 4 and 4, and here, as this particular node, which is node 2, is in between, the element 2 is in between node 2 and node 3, so I have to write here column 2 and column 3, likewise row 2 and row 3. Now finally I am defining K3 matrix. So here for K3, values of A is different. Value of A is given as 100 for this case, into value of E is 200 into 10 raised to the power 3. Then value of length is 150. So I will try to write it once again. 100 into, something is wrong over here. Sorry for your inconvenience. So I will erase this particular portion. Okay. Now this is length. Now we will have area. So area is 100 for this case, into 200 into 10 raised to the power 3. So this is the value of constants AE by L into 1 minus 1 minus 1 and 1. So from this, as I know that I need to keep constants outside, so I'm taking 10 raised to the power 5 outside, and what value which is remain is 1.33, which I have to take inside. 1.33 minus 1.33 and 1.33. Okay, so as this is element number 3 and this element is in between node 3 and node 4, so I have to write here 3 4 column wise as well as row wise, 3 4. Okay, now finally I am having k1 k2 k3 all local stiffness. Now I need to combine this as k matrix. So k matrix, which is called as global stiffness matrix, I have to define this global stiffness matrix by combining k1 plus k2 plus k3. So here I am taking 10 raised to the power 5 common, and before I just place all these things, so all the element to its position, I will write here first 1, 2, 3, 4, and here also column wise 1, 2, 3, 4, so that I can place the particular element to its place. So this is 1 1 position, and here you will find, if I will write k, if you can see k matrix, k1 matrix, then this position is at 1 1. So I have to write this element over here 4. Then this is at 1 2 position. So this is minus 4, here minus 4 and 4. So you have to place each and every element of local, which is in local form to global form to its place. Now this particular element is at 2 2 position. So this is the 2 2 position where you can keep the this particular element. Then this is 2 3 position. So I am just keeping over here 2 3 position. Likewise, then third position, this is 3 2 position, so minus 4, and here it is 4. Now finally I will write down this element to its place. So it is at 3 3 position, so 3 column 3 and row 3. So this is the position where you can keep your element. So this is the position, like I will write 1.33 minus 1.33, then minus 1.33 and 1.33. Okay, so this is how you have defined, and wherever there will be no element, I have to put 0 over there. So here no elements are present, so I will conclude it by, I will write here 0. So this is called as global stiffness matrix. Now finally I will have one relation, like what I have. the stiffness matrix, which is represented by K matrix. So K matrix into displacement matrix, which can be defined as Q matrix, is equal to F matrix, which is force matrix. Now, before just defining the elements, let's see what is given here. As there is a support, so here we will have reaction force. Here at node 20 kilonewton is given at node 2. At node 3 we don't have force, so we need to consider this as 0, and at node 4 it is given as 10 kilonewton. Now what about the displacement? So I have to assume here at node 1 we have displacement as q1. At node 2 I am assuming that displacement will be q2. At node 3 q3, and likewise at node 4 we are assuming that the displacement will be q4, right? So this is all about the displacement at different nodes and the reaction or forces at different nodes. Now I am going to define the K matrix first. So already we have K matrix. So 10 raised to power 5 common for that matrix, and we will have that matrix. So I am just writing the elements 4, then minus 4, 0, 0 column wise, then minus 4, sorry, minus 4, this is minus 4, then 8, I will erase once again so that, sorry, then minus 4, 8, then minus 4, and here 0, then 0, minus 4, 5.33, and here minus 1.33, and lastly I am having 0, 0, minus 1.33, and 1.33. So this is K matrix, right? K matrix multiplied by, here I have to write value of Q. So what are Q? So Q1, I will write Q1, Q2, Q3 and Q4, as these are displacement at different nodes, and after that I am writing defining force. So here at first node it is R or R1. Then at node 2, what is given in the problem, it is given as, so at node 2 you can see 20 kilonewton at node 2, 0, then 10. So 20 kilonewton at node 2, so 20 into 10 raised to the power 3, then 0, and then finally at node 4 we will have 10 kilonewton. Okay, so this is what is given. Then I am using elimination approach. That means at node 1 is fixed, so I am going to eliminate row 1 and column 1 from the final matrix. So I am just eliminating row 1 and column 1. Okay, so after eliminating, only this portion is remain, so this much element are remain. So I'm just highlighting these elements, so this much elements are remain, and from that I can write equation. So what I can write, I'm having three equations, 10 raised to the power 5 common, so 8 q2, so 8, this is 8 q2 minus 4q3 will be equal to 20 into 10 raised to the power 3. This is equation number 1. Likewise, equation number 2 will be 10 raised to the power 5 common. So minus 4 q2. So minus 4 q2 plus 5.33 Q3 minus 1.33 Q4 will be equal to 0, right? Then this is equation number 2, and finally we will have equation 3. So here we will have minus 1.33 Q3. So I am writing minus 1.33 Q3 plus 1.33 Q4 will be equal to 10 into 10 raised to power 3. So this is equation 3. Now if you will solve these three equations, so you will find there are three unknowns and three equations. So we can easily find out the value of the unknowns, which are, so I have found the value of Q2 by solving these three equations. So Q2 can be written as 0.075 mm, Q3 is zero point 0.1 mm, and Q4 finally it is 0.175 mm. So in second video I have I have found all these terms by using numerical method. I have used 18.2. So please see my second video in which I have calculated the value of displacement at different nodes by using NSYS software. Right? Thank you very much.